Chapter 26 is going to tell us all about capacitors and dielectrics. And we're going to concentrate mainly on this capacitor part. Now, capacitor is some kind of device that's used to store charge. So we're going to stack charge onto a capacitor. We can calculate a number that describes the capacitance, or how much charge something can hold, as C, the capacitance, is equal to the charge Q divided by the potential divided by the voltage. So capacitance is the charge divided by the voltage on some kind of device. As a little side note, I find fractions harder to remember when I'm trying to learn these equations, so I always just remembered Q equals CV. That seemed easier for me to remember. Keep that in mind. Now the units of capacitance, the SI units, are going to come from the SI units of charge, which are coulombs, divided by the units of voltage, which are volts. So the units of capacitance are coulombs per volts, which has a special definition. We call that a farad, with a capital F. Now, if we're trying to make a capacitor, we usually want to make a capacitor from a pair of conductors, and the most usual example that you'll see is something called a parallel plate capacitor. So I take two parallel conductors, two metal plates, and I put a bunch of charge on each one. Maybe a bunch of negative charge up here, so I have some kind of negative Q, and some kind of positive charge on the bottom plate. Some kind of positive Q. Now that's going to set up an electric field. And that electric field is going to depend on the distance between these two guys, these two plates, and the voltage across these two plates. There's some kind of voltage that's going to be set up because of the electric field that's flowing here. Some kind of voltage, we'll call it delta V. And I can describe the capacitance between these plates. The capacitance is equal to, still, the amount of charge on one of the plates divided by the change in the voltage between the plates. But I can also describe the capacitance geometrically. In a capacitor, the capacitance you have depends on the geometry that you're working with. In this case, the capacitance would be equal to the area of a plate times epsilon naught, all divided by d, the distance between the plates. So these are just two alternate ways that we can describe the capacitance of a capacitor. Sometimes we know the charge and the voltage. Sometimes we just know the geometry of the plates. We know the area of the plates and the distance separating the two. If we're trying to study capacitors and you open up an electrical circuit, because these things are practically used all over the place, what you'll see is a big cylinder. This cylinder, believe it or not, is actually two parallel plates. It's the same kind of capacitor that we were just talking about. And like I said, you'll see these kinds of cylinders inside of a camera flash, inside of a TV, inside of a radio. Basically anything there's an electronic device, anywhere there's an electronic device, you'll see a capacitor that looks kind of like a cylinder. Now, how do we get that? First, we take our parallel plates. We have two plates. And then we fill it with some kind of material, some kind of insulation. So what I have here is a parallel plate capacitor. I have some negative charge on one end and some positive charge on the other. Now I can take these two plates, and I can roll it up. So imagine folding it, rolling it up, kind of like a fruit roll-up. And when we do that, we end up with a capacitor. We end up with an overhead view of this cylinder where we have one plate on the outside, we have a bunch of insulation, and then we have our other plate on the inside. This is kind of the fruit roll-up view. You can see an example of this in figure 26.3 in your book. And what we do to charge up this capacitor, connect one side of the plate to a positive terminal on the battery and the other side to a negative terminal. So we have a positive plate and we connect the inside of that conductor, that capacitor, to a negative. So we're going to put some charge onto this, and this can actually hold a very dangerous amount of charge. This holds a lot of charge. And when I'm actually working with these capacitors, I want to take a look at how I can combine them to make them store any amount of charge that I want. I have options. I can use a standard capacitor, and there's a bunch of capacitors that you can just go to the store and buy. And you can use these. Their capacitance is going to be equal to Q divided by voltage. Charge divided by voltage. Now the standardized capacitors that you can buy all have a specific C. So what if there's a C, a capacitance that you need to charge up to, that one of these standard capacitors doesn't meet? You could get a specialty capacitor. You could design your own with the right area and the right distance between plates to make the capacitor work for you. But that's going to be very, very expensive. Anything that's specialized is going to cost you lots of money. So what we figured out how to do is how to combine capacitors. And we take these standard capacitors that you can buy anywhere, and we combine them so that we can store any amount of charge that we want. And when we're combining capacitors, what we're going to write to describe how to combine these and to visualize it are something called circuit diagrams. And inside of these circuit diagrams, a capacitor has a very specific picture, representation. We have a wire that comes in, and then we draw two parallel lines, and then a wire that comes out. So we have a wire, these two parallel plates, these represent a capacitor. This is the symbol representation for a capacitor. If you looked at a wiring diagram that comes with your TV manual, you would see a circuit diagram that looks like this. These parallel plates are your capacitor. And then we have the wire coming out. So get used to these representations. You're going to be drawing these kinds of circuits. Now, when we're trying to reach a specific capacitance when we're combining circuits, we can do so by combining them in parallel versus combining them in series. If we combine two circuits in parallel, two capacitors in parallel, this is what we look like. We have a wire that comes in, and then we give it two different options, two different parallel paths that it could follow. It could go through my first capacitor, we'll call C1, or it could turn the opposite direction and we could go through C2. So I have two different choices for where my current can go in this circuit. I could go to the left or I could go to the right. I can split my current between either of those. And then what we do is we finish off this circuit to have a complete circuit. Finish off this circuit by connecting it to this little symbol right here, a long line followed by a short line. This is representation of a battery. So we have a positive terminal of a battery and a negative terminal. So that's my circuit diagram for a battery. And I can look at this and I can see that the top plate of each one of these capacitors, they're both connected to this wire, and this wire is connected to the positive plate. So if I want to label my capacitances, my capacitors both have connection to the positive side of the battery at the top, and at the bottom they both have a connection to the negative side of the battery. And I can follow that negative plate, follow my wire down, connected to the negative plate of my battery. Negative side of the capacitor connected to the negative plate of the battery. So what this really means, that in parallel, my capacitors have the same voltage. And what I'm going to do to figure out the total capacitance that I get in this circuit by combining these two capacitors in parallel, I'm going to add them together. So I need to know the total voltage that's in this system. I'm going to say this battery has a voltage of V. So I can calculate the charge that's on each one of these capacitors. Remember, Q in general is equal to capacitance times voltage. So the charge that's on the first capacitor is equal to the capacitance of the first capacitor times the voltage that it has. And this capacitor, C1, is connected to the positive and negative sides of my battery, so it gets the total voltage of the battery. So charge 1 is C1 times V1. Similarly, charge 2 depends on the capacitance of the second capacitor times the total voltage of the battery. Again, my second capacitor, C2, is connected to the positive and negative sides of the battery, so it gets the total voltage V. Now I need to figure out what the total charge is in this circuit. We know charge is conserved from previous chapters, so we know that the total charge that we have inside of this circuit has to be equal to the charge on the first capacitor plus the charge on the second capacitor. And I can just plug in for my charges. I'll plug in terms of the capacitance to find the total capacitance, or the total charge, is equal to C1 times the voltage on the first one, just V, plus C2 times the voltage on the second capacitor. So my C total, my total capacitance, the capacitance I get from combining these two, times the voltage, is equal to C1 times V plus C2 times V. My voltages are all the same, so my voltages, they all cancel out, and I find that the total capacitance, if I combine in parallel, is equal to C1 plus C2. If I'm adding capacitors in parallel, the total capacitance is just the sum of the individual capacitances. Now, the second way I can combine capacitors is I can combine them in series. So I'm going to take a battery, run a wire up, and I'm going to draw one capacitor C1, and I'm going to draw another capacitor C2. I have my positive side, so I have a positive plate, and I have a negative side of my battery, so I have my negative plate. That negative plate. So to analyze what's going on here, I know that both my capacitors, C1 and my capacitor C2, we'll label that for you. Both my capacitors are not connected to both sides of the battery. This plate, this other plate of my first capacitor, isn't directly connected to the negative side of the battery. Alternatively, this positive plate, this other plate on my second capacitor, isn't directly connected to the positive side of the battery, so we don't have the same voltage. What we do have is this positive plate is going to induce some charge. So what kind of charges are we going to get on this second plate of the capacitor? We're not going to want the same charge. We're going to attract the opposite charge, because the opposite charges attract. And by the same token, this negative side of the plate is going to induce some positive charge on the other side of on the other plate. So this is what our circuit looks like. We know that the voltage in the capacitors is not the same. But it turns out that the charge on each capacitor is the same. Furthermore, we know that the total voltage that's inside of this system, the voltage that the battery supplies, has to go between V1, the voltage through the first capacitor, plus the voltage through the second capacitor. These two voltages have to add together to give me my total voltage. Okay, so I'm going to work with this a little bit. I'm going to work with knowing these things. I'm going to work with knowing that V total is equal to V1 plus V2. I'm going to do that in terms of equations. I know that the charge on the first capacitor is equal to the capacitance of the first one times the voltage on the first one. So since I have hindsight, I know that I'm going to want to put these things in terms of voltages. So I'm just going to go ahead and divide both sides by C1. So my C1s cancel and end up with Q1 divided by C1 is equal to V1. And I'm going to do the same thing for my second capacitor. Charge in my second is equal to capacitance of the second times voltage of the second. Divide both sides by C2. C2's cancel on the right hand side, and I end up with V2 equals Q2 divided by C2. The other thing that we know is that the charge on the first capacitor is equal to the charge on the second capacitor. Charge 1 equals charge 2, and that charge is the total charge within the system. Alright, so what I can do is I can take this voltage total. I know that voltage is equal to charge divided by capacitance. So I'm going to do this and write this charge over capacitance equation for my total voltage. My total voltage has to be equal to the total charge divided by the total capacitance. And that's equal to V1, which is just charge 1 divided by capacitance 1, plus V2, where V2 is charge 2 divided by capacitance 2. I'm going to take this equation that we have, Q total over C total equals Q1 over C1 plus Q2 over C2, and recognize that Q1 is equal to Q2, which is equal to Q total. So I can rewrite this as Q total divided by C total is equal to Q total divided by C1 plus Q total divided by C2. I have Q totals in every element of this equation, so those cancel out, and I recognize that in series, 1 divided by the total capacitance is equal to 1 divided by C1 plus 1 divided by C2. So if I want to add capacitors in series, I need to be prepared to work with the reciprocals. You want to practice with this adding in series approach. And something that will help you is reading the problem-solving techniques on page 837. The last thing we want to talk about in this chapter is how do we improve capacitors. And we improve these with something called a dielectric. And this is a material that you put between the plates of the capacitor. So this was the insulator that we were talking about. What is an insulator that you put between the plates? So the insulator, the purpose of that is to restrict charge flow. It decreases your electric field. And if you decrease your electric field, it turns out that you increase your capacitance. So the electric field between the capacitor with the dielectric ends up being equal to 1 divided by this number called kappa times the electric field without a dielectric. And this letter kappa is kind of a dielectric constant. It changes for different types of materials that you'll use. So it decreases the electric field, but it ends up increasing your capacitance. So capacitance for a dielectric, C, is equal to kappa, the dielectric constant, times the capacitance in free space. So we're going to call that C naught. That's what your book calls it. Okay. So kappa, the dielectric constant, if you have a good dielectric, is going to be greater than 1. The greater than 1 you are, the larger your dielectric constant, the better your capacitor is going to be. How does this work in picture form? If I draw a parallel plate capacitor, store a bunch of negative charge up top, and store a bunch of positive charge down bottom. And I have my electric field that gets set up. If I put a dielectric field inside of this, a dielectric material, then there's going to be a bunch of little atoms inside of here. And due to induction, we know something's going to happen to the charges in these atoms. These charged atoms, or molecules, are going to set themselves up so that there's more negative charges down at the bottom, because these negative charges are going to be attracted to the positives and repelled by the negatives up top. And then the positive charges are going to do the same thing. This is going to be charging by induction. So we're charging our dielectric material, our dielectric atoms, and that's going to set up something called a dipole field. Inside of this atom. It's going to separate our charges out by induction. And the result of this is going to be each little atom is going to have its own little electric field that's going to go the opposite direction of the electric field between the plates. So I can put another dielectric atom in here, dielectric material, positive charge up top, negative charge attracted to the bottom plate, and we'll have an oppositely directed electric field. So these electric fields, the one between the plate, is going to be decreased a bit by the one inside of the atoms. So we decrease the electric field, E goes down, and C, the capacitance goes up. when we use a dielectric. And it's because of this exact picture that we see right here. The last little thing to make note of, and we're gonna work without dielectrics for this case, is figuring out the energy inside of a capacitor. Because that's really how we use them. We use them to store and release energy. The energy inside of a capacitor can be described in a bunch of different equations. We can describe it, energy as 1/2 charge times the change in voltage between two plates of a capacitor. Or we can shuffle things around and solve for charge in terms of capacitance and find U is equal to 1/2 C times delta V squared. These are all equivalent ways to describe the energy of a capacitor. We're just using different variables. We're doing changes of variables. Very easy to do. I can show you how we do this if you'd like in class. Just ask me to. Or we can describe the energy in a capacitor as 1/2 Q squared divided by